Is this what other people got? Just to verify. Okay. Yeah, these are the right orders of magnitude for sure. But when you see 10 to, a k, an equilibrium constant of 10 to the minus 36, what do you automatically think? Small number, big number, what? Very small, which means it's all reactant or all product? It's all reactant. 10 to the minus 36 means it's practically all reactant. I mean, there's barely any product. That has a delta G of plus 200. A delta G of plus 200, it's positive. Positive 200 means it's non-spontaneous. Well, how non-spontaneous is this reaction? Extremely non-spontaneous, right? And so if you have a delta G naught value of plus 200 kilojoules per mole, that's highly non-spontaneous. You aren't going to expect much reaction to be happening there. Even at plus 100 is 10 to the minus 18. It's all reactants too. It's not until you get down to like plus 50, around a range from plus 50 to minus 50, then we have more significant quantities of both. You know, and so over here, you know, when we go above here, around above plus 50 or so, you know, it's practically all reactants. Not all, but nearly, let's say nearly all reactants. The higher up we go, the less product we expect. On the opposite extreme, you know, minus 50 and below, you know, this is 10 to the 17, 10 to the 35. This is all products, right? And so we'll just say nearly all products. And so if we got a delta G naught of minus 150, wow, that's a very spontaneous reaction, right? Should be pushing it to equilibrium. Whereas over here, we're closer to equilibrium. You know, in other words, this is not equilibrium. All these are going to be at equilibrium. We're closer to a mix of or balance. So both reactants and products are significant at equilibrium. And so this we could calculate. Okay, in fact, we could also use this form here. We can just do some manipulation, because this is one way we could solve this equation. Another way that we could solve this equation is like this. We could solve this for ln of k. That is, ln of k is equal to minus delta G naught over RT. The two variables here, K and T, we could look as two variables that are dependent on each other. And so we know that, you know, at different temperatures, like for example, this is at 298 because from appendix D dated, that's what we're going to get. We get at delta G naught. We could do this at other temperatures as well, because we know how to calculate delta G naught at other temperatures. So this is one way we could do this, but the problem with this is this, right? You look at that delta G naught. Delta G naught depends on temperature. And so if we change the temperature here, we also have to change the delta G naught value here. Well, is there a way to make that less temperature dependent? There's something else we could do. This gets tricky. So this would be K at temperature T. This has to be delta G at that temperature T. Now, we can calculate delta G naught at other temperatures by using what equation? Well, the second law of thermodynamics, and that is, if we use this and we substitute this delta H naught minus T delta S naught in here, over RT. Could that get us anywhere? Okay, then we just raise that to the e power. So we could get this. We could get an equation like this. K is equal to e to the minus delta h naught minus t delta s naught over RT. Well, you know, we didn't have to do one equation for this. What we could have done is we could have just solved for our delta G naught at some other temperature using this equation separately and just do it in 2 steps rather than do it in 1 step, shown here. And so we just got to make sure the 2 t's match here, and then we can calculate it here and here. So t's match. But didn't we do some other equation? Celine, didn't you solve for some other equation in which we had the temperature?
It was pretty much the same equation except we solved for temperature. The temperature would be at a certain pressure.
Mm-hmm.
And then we did the same thing where instead of solving for the temperature, we solved for pressure. And in that equation, pressure is in literally the same spot with this K constant.
Okay. Well, let's think about this. Maybe what we could do is we could try something like this. We do ln of K and then come up with some equation ideas. Ln of K at temperature 1 is equal to minus delta H naught. Well, delta H naught should be at, actually, we'll just call it T1. Delta H naught should be at T1. Minus T1 delta S naught, which should be at T1. This is going to be divided by R T1. Okay. Then we'll try to simplify this by saying, well, maybe delta H naught at T1 is close to delta H naught at 298. So we'll just say this is going to be about equal to delta H naught at 298 minus T1 delta S naught at 298. Assuming that delta H and delta S don't change much with temperature. This will be divided by RT1. Here. All right, and so what we'll try to do is we'll try to do something like this. We'll try to do ln of K at T1 minus, well actually let's do ln of K at T2. We'll do ln of K at T2, which would be a different temperature than T1, is equal to ln of K at T2 minus ln of K at T1 is equal to, we'll just subtract these 2 terms here. And so what we'll do is we'll get the one for T2, which would look just like this, except we're going to have it minus T2 here, delta S naught at 298 Kelvin, divided by R T2. And then we'll do a minus delta H naught at 298 Kelvin minus T1 delta S naught at 298 Kelvin over R T1. Does that get us anywhere? Let's see. Well, using the property of logs, ln of K at T2 over K at T1, so we set up a ratio of the equilibrium constant, is equal to this minus this. Well, that's not going to help us, is it? So much if the math looks this complicated. And so let's see if we could simplify this. The way we could simplify this? So looking at this, okay, minus delta H naught at 298 minus a minus delta H naught, except these don't, huh? Yeah, because the denominator is not the same. So this doesn't work. This doesn't work, unfortunately. So have to come up with some other form to come up with some other relationships. So this is the part of thermodynamics that's tricky, is coming up with these relationships by rearranging things and coming up with new equations. And so we'll come back to this one. This one is, think about this. Let me think about this. And why don't you think about this, and then we'll see. All right, so if we have delta G equal to 0, that means the system's at equilibrium. And if it's at equilibrium, that means K is equal to minus delta G naught over RT. Okay, but what if delta G naught is equal to 0? If delta G naught is equal to 0, that means it's at equilibrium, right? If it's at equilibrium, then that means that K is equal to 1. And so, well, what does that mean? Well, that means this. If K is equal to 1, that means the activity of the products raised to, you know, dot, 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 A, B, C, over the activity of the, actually this would be G, activity of the reactants is equal to 1. That means all the concentrations are 1 molar, and all the pressures are at 1 bar or atmosphere. And so when do we get a delta G naught equal to 1? Well, when K is equal to 1. And so when we think about delta G naught is equal to 1, we think, under what conditions is the equilibrium constant equal to 1? How often, oops, delta G equal to 0. How often do you see this? Is it common or is it rare that a K is equal to 1? What's that?
Well, the sum of all thermodynamic forces, so delta G of the universe should be equilibrium, right?
Well, this is just for, we're looking at the system. We aren't looking at the whole universe, because this is just delta G naught for a system. And for a system, it doesn't matter what's happening with the rest of the universe in this case. And so for the system here, actually it accounts for it, but for the system, this is rare at 298 Kelvin. It's rare at 298 Kelvin, but we can do it. For example, you know, when we look at H2O liquid goes to H2O gas, you know, delta G naught was, you know, plus 8 kilojoules per mole. And so that's non-spontaneous. But what we did was we set delta G naught. You know, delta G naught changes with temperature. And what happened was we got delta G naught equal to 0. You know, but the temperature is at elevated temperature at T boiling point. And so this way, what we did was here, when we think about the delta G naught is going to equal minus RT ln a K. And therefore K is equal to 1. K for this is just equal to the partial pressure of the H2O gas. So the H2O gas is at 1. And so what we see is this. When we look at the delta G knots, you know, the greater it is above 0, you know, the farther the equilibrium conditions are. The farther the initial conditions are from equilibrium. Actually. And so, I'm sorry, this got a little bit mixed up. It wasn't presented the way I wanted to present it initially. But we'll come back to that earlier problem. And so to give this some thought, you know, what it means for delta G equal to 0 and delta G naught equal to 0, let's take a look at some problems here. So I just posted this. This is an old exam from 19. Why don't you take a look at problem number 1 and then see if you can come up with the answer to that.